All right, so we're recording the session as we speak. So you want to do Q&A. Okay, so another person wants to go through the slides. Okay.
I think it would be helpful to go through the slides.
All right, so just do like a regular lecture, which is fine. We can do that. This is technically what this is. So for those of you who already watched the videos, that's just, this is going to be a little bit of a review. And for those of you who did not and prefer to have a live lecture, then I'm happy to do a live lecture. And if you prefer that, we can just moving forward, just do a live lecture because technically the slides are in front of us and I can just lecture and I can actually write on them and the whole thing. So let's try that for today. I apologize if you've already watched the videos and this is going to be sort of reinforcement at this point, which is not a bad thing. Let's try and see if this is going to be the best approach. So this is where we had left off last time. Let me then move forward to the next slide. So the topic that we, let me just recap the previous topic very briefly. Unfortunately, the clicker questions are, unless I figure out a way, I know there's sort of a way to do live questions. I still have to figure that out. So for now, we're not going to do clicker questions until I figure this out. Let me just go back to this concept, which is the last concept we talked about before we went on break, which is the concept of atomic size and how that influences acidity. So the bottom line for that is that if you're looking at different acids and the atom from which the proton is being removed from have different sizes, then the one that has the larger size will provide the more acidic compound. And we had left off talking about this particular question, so which compound was more acidic? In this case, if you notice, this proton is bonded to an oxygen, this proton is bonded to, I need to close these little things so that I can type. This proton is bonded to a sulfur, and therefore this particular compound happens to be more acidic. This proton is easier to remove than in the compound on the left because of the larger size of the sulfur. All right, so that's sort of where we had left off. The next topic that we needed to discuss was resonance. Resonance has a huge impact on the acidity of compounds, and if you compare these two compounds that I'm showing here in the center, the first one on the right, on the left, excuse me, is acetic acid. The one on the right is ethanol. And if you notice, in both cases, the proton is bonded to an oxygen. Now, the main difference is that there's an additional component to the acetic acid. And what happens is that when that proton is lost, what is produced is the structure that's on the bottom left, which is acetate. And if you recall the concept of resonance, when acetate is formed, you have the ability to delocalize that charge. I don't think this has a highlighter, so I can't do much other than just kind of write on top of things. But what happens is that the charge can be spread out over these two oxygens as opposed to just one oxygen. That is, on the case of the conjugate base of the ethanol. So because this charge is pretty much stuck on oxygen, we call that a localized charge as opposed to spread out over two oxygens. This is what we call a delocalized charge. Then this is a much more stable outcome. Therefore, the loss of the proton from this compound is much more favorable, much more likely. And this is why when you compare the pKa's of these two compounds, the acetic acid has a much lower pKa, which is what makes it a much stronger acid than the other one. If you do the difference between these two pKa's, if you round this one to 5, the difference between 16 and 5 is 11. So what does that mean? It means that it's a 10 to the 11 orders of magnitude difference in acidity. So what that means is that acetic acid is 10 to the 11, which is 100 billion times more acidic than ethanol. And that has entirely to do with the ability of the conjugate base of the acetic acid to delocalize that charge, making that structure much more stable, and therefore that then makes the corresponding acid a more acidic compound. Okay, so this is the concept of resonance. All right, so again, here would be a question that if we were in a live classroom, we would ask. looking at vitamin C. Vitamin C is a relatively acidic compound. In fact, the generic name, the scientific name of vitamin C is ascorbic acid, and it has a pKa of about 4.2, which is comparable to a carboxylic acid. And if you look at the structure, there's no carboxylic acid anywhere on this structure. So the question is, which of these two protons, the one that's highlighted in red or the one that's highlighted in blue, is going to be the most acidic of the two protons, the one that actually gives the compound the acidic nature and the name ascorbic acid. So in the next slide, we're going to analyze the outcome so that you can then observe why one is more acidic than the other. So if you look at the next slide, we have the structure. So what happens, let me use the proper color coding here. I'm going to use red for the left. So if this proton is lost, suddenly you end up with a negative charge on this oxygen, and that pair of electrons that was holding on to that hydrogen is retained by the oxygen as a lone pair. So let's just use the negative charge as the equivalent of the lone pair. So what happens? If you remove that proton, that charge can sit on oxygen to begin with, then it can actually resonate to ultimately be shared by that oxygen that's on the far top right. And what that leads to is the formation of a alternative structure, which I'm going to attempt to draw here with my little electronic pen. One of the good things about this whole thing is that we're now learning to use all sorts of technology, right? So the charge can end up on that carbon at the end over there. Because this piece is irrelevant, I'm just going to put an R group to represent that. These two protons on these two oxygens, there's no possibility of delocalization once they're lost. So because of that, they're not even considered in the discussion. If you then, you get this structure. So you'll notice that the charge is sort of distributed amongst these atoms. It's spread out over that whole portion of the structure. If you, on the other hand, consider some base coming over here and removing this proton, what that results is, again, loss of this proton. That pair of electrons ends up here as a lone pair. And then all that can happen here is that this forms a double bond there, and then this pair of electrons simply ends up on that carbon as a lone pair on carbon. So let me redraw the structure that results from that outcome. And what you get is this. This piece simply remains as it is. You end up with a lone pair on this carbon. This whole R group simply remains where it is. So the main difference is that the charge is now shared over these three atoms as opposed to these 5 atoms. And in this case, 2 of them were oxygen. In the other case, one of them is oxygen, the other one is carbon. So carbon is not as electronegative as oxygen. This is not the best outcome. So therefore, this compound on the left, the structure on the left, is the one that's most likely to form. Therefore, this proton over here is the one that is most likely to be removed. That is the proton that exhibits the pKa of 4.2. Okay, so I'm not sure how to deal with people lifting up their hands for questions. People have commented things in the chat, so let me see what I'm seeing. Just bear with me as I read through the things. This is just the comments that if people want to go through the slides, then that's fine. This is what we're doing. Okay, so if that's what most people want, then that's fine. All right, so everybody's with me. Let me clean this up again because this is a big hot mess over here right now. So again, this proton is the most acidic because once that proton is removed, the charge can be spread out over all of these atoms, and 2 of them are oxygen, and therefore that produces a more stable conjugate base. Therefore, that proton will be the one that exhibits the lowest pK. So somebody, Delara is asking a question. Well, the question I have, does oxygen make the double bond because it's more electronegative? So the point, in this case, two things are technically combined. This double bond is between two carbons. This double bond is between carbon and oxygen. The loss, let me clean this up so that we can do it again really quickly. The loss of this proton produces, again, this structure. There's an oxygen with a negative charge. I'm going to put this R group here. And then we have this structure, right? So this produces a double bond there. Technically, I sort of skipped this. Technically, there's an additional resonance form in which the charge ends up initially on this carbon. And then from there, it ends up on the oxygen at the end, right? Like this. Negative charge there, double bond there, doubly bonded oxygen here. So that's how you can then see that the charge sort of resonates between this oxygen, this carbon, and this oxygen, which is this oxygen, this carbon, and this oxygen, ultimately spread out over all of this. And that's what makes this the one that's more likely to. And yes, the electronegativity of the oxygen is a huge factor, because the fact that you can have that charge spread out over two of the atoms are very electronegative, as opposed to the other case in which only one of them was the electronegative oxygen. That makes an enormous difference in the acidity of the structure. Okay, all right. So now I have actually, I figured out that I have the chat window open. If anybody has a question, you can just pop it right in, and as I go through the slides, I'll kind of glance at the chat section, and then I can answer any questions that come up as I'm going through this whole thing. All right. So there's another important sort of last effect that we need to talk about, which is what is known as the inductive effect. And this is when there's the presence of electronegative atoms somewhere along the skeleton, the structural framework of the compound. And the number of electronegative atoms and the proximity of electronegative atoms, or a combination of those two things, directly affects acidity. So if you start here on this slide looking at the compound that's on the far left, let's use that as our reference point. This is, again, acetic acid. This has a pKa of around 4.75. If we replace one of the hydrogens, remember there's 3 hydrogens here, right? 1, 2, and 3. If we replace one of those 3 hydrogens with a chlorine, so now there would only be 2 hydrogens and 1 chlorine. Well, the chlorine is highly electronegative. So what that does is that it attracts electrons toward itself. That's what that little red arrow that's there is trying to indicate. And what that does is that the moment this proton is lost, that negativity that arises from the loss of that proton, that still resonates between the 2 oxygens like it does with regular acetate, but now that negative charge, let me change colors here, I'm going to go back to blue, that negative charge is now sort of attracted towards the chlorine. The moment charges can be attracted to somewhere that stabilizes them, like an electronegative atom, or resonance that spreads them out over several atoms, all of those issues, structural features, lead to stabilization. In this case, both of them are operating. The fact that the charge can be delocalized between the 2 oxygens is an important stabilizing factor, as we've discussed in the previous slides. But on this case, when you compare the second compound with acetate, the presence of the chlorine adds an additional level of stabilization because of that attraction, and therefore that's what lowers the pKa a little bit more. Now notice the effect is not as dramatic as with resonance. Again, if we go back for a moment, we compare the effect of the presence of that carbonyl, which introduces a resonance effect, compared to not having it. This is a pKa difference we already established. It's around 11, which means a 10 to the 11 difference. Much, much more significant, much, much more dramatic than if you simply consider a inductive effect. The presence of the chlorine is going to lower the pKa by about 2 points or something of the sort, which is 10 to the 2, which is 100. So 100 billion is not the same as 100 times more acidic. Now, as I said, the number of atoms also contributes. If you have now 2 chlorines instead of 1, then notice the pKa goes down yet another point and change, so it makes the compound even more acidic. If all 3 hydrogens are replaced by an electronegative atom, i.e. chlorine, then that even further lowers the pKa. Now, in this case, because there's only 1 carbon on the left of the carboxylic acid, the distance effect is not observed, but I think there was a question coming related to that. So if we look at this question, for example, which of the, if you look at the 2 on the left, right, this is 2 different compounds, two pairs of compounds. So if we start on the left, which one's more acidic, just by looking at it? Well, you notice everything, the skeleton is pretty much the same, the carbon skeleton. The difference is this one has only 1 chlorine, this one has 2 chlorines, right? So therefore, 2 of them, they're in the same position, 2 of them is going to enhance the acidity of that compound. So this is the more acidic of the 2 compounds. In the case of the right compound, let me change colors here. In case of the right compound, the carbon skeleton is again the same, but here what you observe is the proximity issue, the distance issue. This one is 1 carbon away from the carboxylic acid. This one is 2 atoms away from the carboxylic acid. So therefore the effect is determined by distance as well. This is going to be the more acidic of the 2 compounds because the bromine is closer to the carboxylic acid. Here it's further away, so that effect dampens. It actually gets to the point where if the electronegative atom is too far away, the effect ultimately kind of dies off and it doesn't have much of an effect once you get more than a handful of atoms away. So I think we had a clicker question at this point, which we're just going to go through it. So the question was, here's one of the amino acids that we're going to be learning about once we start talking about proteins and things of the sort. So which of the 2 protons is more acidic? So Allison was asking, while you guys think about that for a moment, if we're comparing structures, one that has resonance will be stronger acid compared than one that has inductive effect. The answer is yes. All else being equal, if one has resonance, another one does not have resonance, the one that exhibits resonance will have a much stronger acidity, much higher acidity than the one that doesn't. All right. So if we look at this compound, what you need to observe, we have 2 carboxylic acids, right? And one of them has a nitrogen, which is 1 atom away. This nitrogen is attracting electrons because nitrogen is the second most electronegative element in biological systems. In the case of the the carboxylic acid on the left, which is the red one, the nitrogen is much further away. So therefore, what you would expect is that this proton is going to be the one that exhibits the pKa of 2.1. The second carboxylic acid, which is much further away from the nitrogen, that's the one that exhibits the 4.07 pKa. So the more acidic one is the one that's closest to the nitrogen, the electronegative atom that exerts this inductive effect through the skeleton of the structure. The other one is further away. And notice pKa's of typical carboxylic acids are in the sort of 4 to 5 range. That's more typical than a regular carboxylic acid. This is far enough away that it doesn't exert a huge effect on the acidity. This one, because it's so close to the other one, it has, it lowers the pKa by about a factor of 2, which is about 100-fold more acidic. All right, so oh, we can do that. So somebody's suggests, can everybody see everybody's chatting, or I don't know if everybody else can see or if I'm the only one that can see it. All right, good. Yes, not everybody needs to answer at once. All right, good. So if everybody can see it, then we can do that. We can have you guys sort of, or a handful of you answer at some point, and then we can do that. All right, so here's a question, never a silly question. So does inductive effect apply throughout the whole atom, or is there a set range where it ends? So I'm not sure I understand the question, but let me just, from what I'm understanding, it applies to the whole structure. So the electronegative atom exerts an effect, an attractive effect, throughout the skeleton, the closer it is to the acidic site, the stronger that effect would be. The further away it is from an acidic site, the weaker that effect would be. Okay? All right. All right, let me see. Okay, so sort of pretty much done now with the whole process of understanding the structural features that determine acid-base properties. We now need to actually talk about the process of acid-base transformations and this concept that is known as neutralization. So neutralization is in fact what happens when an acid and a base react with each other. The outcome of that reaction is actually a salt. By definition, a salt is an ionic compound that's neither an acid or a base, okay? And in the case of aqueous systems, then very commonly when we're talking about the Arrhenius definition of acids and bases, in addition to a salt, whenever an acid reacts with a base and they neutralize each other, a molecule of water is also produced as a side product. So what we need to have a little bit of a discussion, and my apologies if the slides are a little bit distorted here from the uploading from the PowerPoint thing as it was converted into this platform. So what happens is that what needs to be considered is what happens to the pH of the solution when you mix equimolar amounts, meaning same number of moles of an acid and a base together in solution. What happens at that neutralization point? So you may think, well, it has to be 7, but it turns out that that's only true when you're mixing a strong acid and a strong base. Because what happens in that situation is that the acid gets converted to its conjugate base, and because it's a strong acid, the conjugate base will be a very weak base. And because it's very weak base, it's not going to do anything with water, it's just going to sit there and nothing much happens. Yeah, I'm thinking probably the bottom of the slide is cut off for everyone. So because I can't see it very well down here. So if everybody actually has the packet of slides, not this one in front of you, but from the PDF that was distributed at some point that was posted on Blackboard, then you can probably see the bottom of the slide that's being cut off right now. On this platform, unfortunately. So this is just trying to illustrate what happens when you mix a strong acid with a strong base. And what's going to ultimately happen is that the pH when it's perfectly neutralized is going to be pH of equal to 7. So if you consider a strong acid, right, what happens to a strong acid? By definition, as we've described, strong acids will completely, meaning 100% ionize into its corresponding proton and its corresponding conjugate base. If you're dealing with let me change colors. If you're dealing with a strong base, typically strong bases, as far as you're concerned, are metal hydroxides. So put lithium hydroxide, sodium hydroxide, potassium hydroxide, things of the sort that you've used in lab at some point and you'll continue to use throughout the rest, well, actually not anymore, sorry, through the rest of the semester. So the point here is that the hydroxide is what is released into the solution. This is what acts as the base. It's a strong base. What acts as ultimately the acid in the solution is the H+. So what happens? This is what these two little things that are kind of screwed up here we're trying to represent. That what ends up happening is that the hydroxide, let me erase this and start again with a fresh color here. What happens is that the H+ that was released from the acid will find the hydroxide that was released when the base dissolves. These two will find each other, and they will then produce a molecule of water, and that is the water that's produced as part of the reaction. What's left in solution? What's left in solution is the conjugate base of the acid and the metal that came with the hydroxide. They find each other, and they simply remain in solution as spectator ions. So all of the acid neutralized all of the base and vice versa. They both technically disappear. They reach the normal 10 to the minus 7 molar that's present in water, and therefore the pH is going to be 7. So somebody asked a question, is it still considered neutralization if the pH is not 7? So the term neutralization, it can be used very broadly. It simply broadly refers to when an acid reacts with a base, very broadly speaking. In this context, what we're speaking of is 100% neutralization, meaning that there is an exact amount of acid and the same exact amount of base. They coexist in equimolar amounts, and therefore they completely neutralize each other. Then the question is, what will be the resulting pH of that solution? So if you have exact amounts of acid and base, they will exist in the same amounts. At that point, if they're both strong, what results is a neutral solution with a pH of 7. You can mix non-equimolar amounts, so a certain amount of base and a different amount of acid. Technically, the reaction that still happens is neutralization. However, is in a deficit, will be completely consumed, and it will neutralize completely a certain amount of the one that's in excess. But then the one that's in excess will remain in excess, and that will then yield a solution that's not neutral. But the annihilation, that's another term, not the correct one, but you can sort of see it that way. The annihilation of any acid present with any base present, that's called neutralization. If they are present in equal amounts, then what you result is nothing. All that results is the salt. pH will be 7 at that point. But that's only true if they're strong. Did I answer that question? Everybody's clear with that? All right. So where it gets a little tricky is when you have weak species in the mix. So if you have a strong acid, still strong acid, again, you get the complete ionization. It forms H plus and A minus. This is pretty much gone from the solution, right? However, if you mix that with a weak base, so the weak base will react with water and an equilibrium is established in which the conjugate acid of the base and hydroxide, to a small extent, a certain percentage, not 100% per mole of base, but only a little bit of hydroxide is produced. So what happens is that now you have the majority of the base still exist as this compound. Only a fraction of it has ionized. So there's only a little bit of hydroxide that is there to react with the H plus, right? So let me clean this up because it's already a mess with these things that are sort of distorted over here. So then what happens is that the H plus will ultimately react with the hydroxide. And then what that produces is a solution that, yes, some water is still going to be produced in the process. That's what's being shown over here. But then what you have at the end is a mixture of the conjugate acid of the base combined with the conjugate base of the acid. And this is what you end up with. Okay, this is what you end up with in solution, plus the water. That's the product of the neutralization. However, what happens now is that, let me try to change colors here. This species, the conjugate acid of the base, and I'm going to write this down here just to make it clear because it's all a mess over here. That conjugate acid of the base, what turns out to happen with that is that it actually ionizes and it restores a little bit of the base and it releases a little bit of the acid that was bonded, the protons that were bonded to that structure. So therefore, at the neutralization point where the entirety of the HA, strong acid, has neutralized the weak base B, what you're going to end up with is this structure coming from the base, which ultimately does this process because it's a weak base. This turns out to be a weak acid. Some H plus is released into the solution, and what that produces is a slightly acidic solution, even if you are at the perfect neutralization point. So the bottom line is that when you mix a strong acid with a weak base at the perfect neutralization point where you have equal amounts of one and the other that they have neutralized each other, what you end up with is with a slight excess of protons coming from the conjugate acid of the base that was formed as part of the neutralization process. That excess bit of acid that is then released into the solution produces a slightly acidic solution with a pH that is slightly less than 7. Okay, so strong acid with weak base will produce a solution that is slightly acidic. Okay, everybody's with me? All right, so let's then continue. I have to shift here because my neck is about to snap in a moment. Oop, sorry. All right, the next scenario would be if you have a weak acid with a strong base. Oop, this is touching my face. So if you have a weak acid, partially ionizes to release protons and a certain fraction of the conjugate base. If you mix that with a strong base, a metal hydroxide, the metal and the hydroxide completely dissociate. So now you have a solution of a strong base in the presence of a weak acid. What happens is, again, the H plus will neutralize the hydroxide. The metal that came with the hydroxide ultimately ends up combining with the conjugate base of the acid. And then what ends up forming, sorry, my dog is here and is trying to be fresh. What ultimately is produced and released into the solution at the neutralization point is the metal that came with the base combined with the conjugate base of the acid. Now, because this is the conjugate base of a weak acid, that conjugate base is itself a weak base, okay? You want to see the dog? Say hi, Max. He's here on my little desk. Say hi. All right. All right. So what happens now is that what you end up with, and I'm going to write it here on the left so that we can see it a little bit better, because again, this is kind of a big mess over here. Sit down. The conjugate base of the acid is now in solution. When that finds water, it establishes an equilibrium. It regenerates a little bit of the acid and then produces a little bit of hydroxide. So sort of in the converse of what happens when you have a strong acid with a weak base, that you end up with a slightly acidic solution. When you have a weak acid that's mixed with a strong base at the neutralization point, because you end up with the presence of the conjugate base of the acid, which is a weak base, a little bit of hydroxide is going to be produced by this reaction shown here, and that then ultimately results in a slightly basic solution for those particular types of compounds. All right. So the last scenario, of course, would be if you mix a weak acid and a weak base. I'm not going to spend too much time on this one. This is typically beyond the scope of this course. The bottom line for this one is the ultimate pH that results at the neutralization point will depend on the relative strengths of the acid and the base. That then determines the relative strengths of their conjugate partners. So if the conjugate acid of the original base is stronger as an acid than this conjugate base is as a base, then the acid wins. The reaction will, the solution will have a slightly acidic pH, i.e. slightly less than 7. If the conjugate base of the original weak acid is stronger as a base than this acid is as an acid, then the base wins. And there's going to be a slightly basic pH, slightly greater than 7. If they, by chance, happen to have similar strengths each on their own, the acid is about as strong as an acid as the base is about as a base, then you end up with a solution that has nearly neutral pH close to 7. And there are examples of salts like that, that when they find each other and they neutralize each other, even though they're both weak, you end up with a pH about 7 because it turns out that they balance each other out perfectly. All right, are we good? Questions? All right. So everybody's here again. There is a way to sort of ask these questions on the fly. I still have to figure that out, and I will figure it out. So we will have. Let me look at this for a minute. We will have a manner to record attendance. I probably can also look at the list of people that are in here, but anyway, we'll deal with that at another moment. All right. Yes. Okay. All right. So we need to talk about some of the important applications of these concepts that are going to bring us into our discussion on biochemistry that's going to be starting at some point soon. So there's an equation that is known as the Henderson-Hasselbalch equation that we need to talk about because it brings us to the concept of buffers, which is one of the most critical concepts that we need to take away from this entire, somebody's typing test in here. So what is this? Oh, they're testing if they can write. Okay, that's fine. All right. Oh boy, this is kind of a mess over here. So what this slide is saying is, let me just kind of sum it up. When you're looking at a solution that has a single acid or base dissolved, let's focus on acids because the discussion is a little bit easier. The pH that the solution of an acid will exhibit is dependent on the pKa of the acid. And that also determines the ratio at which the acid and its conjugate base will exist. When you have mixtures of acids, which is what ends up happening in all of your biological fluids, each acid will contribute a certain amount of H plus to the solution, and the total pH of that solution will be the sum of all, resulting from the sum of all of the hydrogen ions that were produced by all of the acids that were in that solution that contribute to that total amount of H plus in the solution. So as with single acids, when you have mixtures of acids, that pH is going to depend on the pKa's of the acids, but it turns out that the total amount of acid that is in a solution influences how all of the acids will ultimately ionize, and ultimately determines what is the ratio of conjugate base to acid that will ultimately exist in that solution. So the equation that I'm trying to get to is sort of derived here. Let me just, because it's just kind of a mess here. If you remember, never mind the P function, the definition of Ka equals the product of H plus times A minus divided by HA. If you apply the P function minus the log function on both sides, and you do some solving and some rearranging, that's what's shown there. Let's just skip all that and get to the end, which is what we'll need to get to. The next slide shows what is the important equation that then shows the ratio. This is the important piece here, which is shown in a slightly different way in the middle. The ratio of a conjugate base to acid of a weak acid in a solution will depend not only on the acid's pKa, but on the pH of that solution if that pH is controlled externally. So this is what this slide, this is what this jambalaya over here was trying to say. If you have a solution in which the pH is controlled externally, and that means that you have multiple contributors adding H plus to the solution, all of that is what controls the pH. When that happens, then the ratio of any individual acid to its conjugate base is determined not only by that acid's pKa, but by what that pH is, depending on how many acids are in there and how much acid they contribute to the totality of the solution. So if you then rearrange this equation, you'll notice that the amount of conjugate base in a solution is directly related to how much acid is present in the solution. You have to multiply that by 10 elevated to the difference between the pH and the pKa. So this is what's truly important here in this particular, this little table here. This is from the textbook that shows an important piece of information. So whenever you have an identical ratio, an identical amount of a acid and its conjugate base present in the solution, these two numbers are the same, the pH of that solution will equal the pKa of that acid, okay? So it turns out there's another way to define pKa, and that is the pH at which an acid and its conjugate base coexist in an equimolar ratio. Now, the key important piece here, which is we're going to come back to this as we embark in some of discussions that are coming later, and when we talk about amino acids and other important acid-base compounds that we're going to talk about later, is what happens when those ratios are different. So here's the thing. Whenever you have a pH, when the pH of a solution is less than the pKa of the acid, it's more acidic than the pKa, then that means there's more of the acid than there is of the conjugate base. Okay, so this is the way to sort of rationalize this. Let me clean this up because this is a big mess. When the pH is more acidic than the pKa of the acid, in that solution, more of the acid will exist relative to the conjugate base. The converse of that would be if the pH is more basic than the pKa of the acid, then more of the base will exist relative to the acid. Okay, so this is the important piece that we need to understand. We're going to put this together as we move forward. Again, this will make more sense when we start looking at examples of things. All right, so I mentioned that when we actually started talking about equilibrium at the very beginning of the semester, that I mentioned that Le Chatelier's principle is, if you're going to walk away with one thing from this course, it's Le Chatelier's principle, which is what governs pretty much everything in chemistry. Meaning that when you have a system that has reached equilibrium and there's any type of perturbation or disruption, the system is going to respond accordingly to try to counterbalance or counteract that perturbation and then bring the system back to equilibrium. So when we're speaking about acids and bases, let's again focus on acids. Here's a weak acid reacting with water, producing hydronium and its corresponding conjugate base. So again, at a given pH, the ratio at which this and this coexist is going to depend on the pKa of the acid, of course, but it's also going to depend on the pH. So again, what happens if the pH decreases, right? pH decreases, that means that more acid is added to the solution. So if you're adding more of this one, what's going to happen? Well, the system is going to shift to counterbalance that addition or that change in hydronium ion. It's going to shift to the opposite direction. So if you have a greater amount of acid added to the solution, the reaction is going to shift towards consuming some of the conjugate base, making more of the acid. And therefore, the ratio of these two is going to decrease because some of this is consumed and some of this is produced. So if the pH is small, somebody's asking if the pH is smaller than the pKa, there is more acid. You can make the analogy with pKa and pH and the whole thing. Yes, it's very, very similar. So that type of an analogy that you can make. Okay, that's absolutely correct. All right. So if your pH increases, so what happens? Let me change colors here. Let me erase this whole thing. If the pH decreases, so then some of this is lost somehow, less acid, that goes down. So what's going to happen? The system is going to shift in this direction. So more of this is made, some of this is lost. What happens to the ratio of A minus over HA? Well, this is going up, this is going down, right? So the ratio gets bigger, more base, less acid. That's what happens when the pH increases. Okay, so it's just a matter of understanding the process. You have a system at equilibrium and you have a certain ratio of this to this, of base to acid at a given pH. Let's say the pH is fixed. If it changes, if this goes up or down, the system is going to respond accordingly, and more of this one or more of that one are going to be produced. That then affects the ratio at which they coexist. Okay, so we're going to see, actually, so there's going to be some math involved in this particular section, unfortunately. All right, so here's an example of an amino acid. Is a type of biological compound that we're going to be looking at once we start talking about proteins in a little while, in a few chapters. So they're telling you here that at low pH, meaning high acid, this is the structure at which alanine will tend to exist. So the question is, It's asking to redraw alanine, showing the carboxylic acid and the ammonium in their conjugate base, right? So let me just look at this for a minute. Showing the acidic and in their conjugate base form. Okay, so the conjugate, let me get my pencil ready here. This is the acidic form. This is this is the sites where there's going to be reaction, right? So if you then consider the conjugate base of the carboxylic acid, we can write it as CO2 minus. The conjugate base of the ammonium is the NH2. Okay, NH2 with a proton there. So then it's asking if the carboxylic acids have a pKa in the range of 1.8 to 4.3. So this is between 1.8 to 4.3. And for ammonium groups, which is this one, the pKa is somewhere between 9.1 and 12.5. How would alanine appear at pH 7 is the question, okay? So at pH 7, that pH is greater than this one, but it's less than that one, okay? So as we've said, when the pH is greater than the pKa, the more basic form is the one that's going to predominate. When the pH is lower than the pKa, then the more acidic form is going to exist. So in this case, we're talking about a pH that's higher than that one, so the basic form of this one is going to predominate. So I'm going to draw that as the basic form, which is this, CO2 minus. In the case of the ammonium group, at pH 7, the pH is less than the pKa. The acidic form is the one that predominates, which is this one. So NH3 plus is the one that predominates. So the whole point of this discussion is to illustrate that different functional groups will be at different states of protonation versus deprotonation, depending on the pH in which they exist and the pKa of those particular functional groups. If you look in your bodily fluids, pH is between 7.3 and 7.4-ish. So amino acids that are floating around in your blood, the carboxylic acid piece of them will exist in carboxylate form. Why? Because that pH, 7.3 to 7.4, is greater than the pKa of those functional groups. The amino portions of those structures, whose pKa's are 9.1 to 12.5 in your bodily fluids, because the pH is less than, they will continue to exist in their protonated form as shown here. So amino acids in bodily fluids exist as these doubly charged structures. The nitrogens are protonated and exist as ammonium ions. The carboxylic acid pieces are deprotonated and exist as carboxylate ions. And anytime you have a structure that has both a positive and a negative charge in different parts of the structure, those are known as Zwitter ions. Sorry, this is weird, but Zwitter ions. Oh, you know what? I can type it over here. I can type as well. Zwitter, let me see, Zwitter ions. That's the name. Some German name or whatever. Okay, so we're going to see examples of these things as we go along. And one of the things you need to learn is if you're given pKa's of functional groups on a structure and you're given the pH in which that structure exists, what is the most likely state of protonation versus deprotonation of those functional groups in that particular medium? Okay, all right. So why is this important? Again, you may be asking yourself, why are we talking about this? Well, it turns out we talk about things because they're important in one way or another. So let's consider where this really becomes critical is for pharmaceuticals and how your body handles them, how your body manipulates them, how your body absorbs them. So here's a compound that we are very familiar with, which is aspirin. Okay, so aspirin, as you have learned, has a carboxylic acid over here. Turns out that that carboxylic acid has a pKa that's a little bit lower than what you would expect for a typical carboxylic acid. It's because of structural features of the compound. It's about 3. Okay, now it turns out that the pH of your stomach fluctuates somewhere between 1 and 3. Okay, so if the pH is 1, when is your pH 1? Well, the pH is really low when you are in between meals, your stomach is pretty much empty, having no food in it, and you're thinking about food, or you're anticipating food. And you're watching somebody eat lunch and you can't eat lunch, right? And you start growling and whatever. So this is when your stomach is producing lots of acid. So that's when your pH is really low. So if you have a headache at that moment and you decide to take an aspirin, your aspirin, which has a pKa of 3, is going to enter your stomach with a pH that is about 1. So what does that mean? Well, the pH is really low. It's below the pKa. So which of the two species is going to be one that predominates? Because the pH is less than the pKa, the protonated, i.e. acidic version of the aspirin, which is this one, this one here, is the one that predominates, okay? Now, if you notice, this structure is uncharged, does not have a charge. The protonated version of aspirin is a neutral compound. It's polar, it has partial positives and negatives in different places, but as a whole, the structure has no charge. As the pH increases, the amount of this one is the one that starts to appear. And in fact, when the pH is around 3, if you were to take aspirin in your stomach, soon after you've eaten, it turns out food serves to neutralize the acid in your stomach. So that's when you ingest a meal, that's when the pH starts going up, right? So if you have your meal and then you take your aspirin, at that point, the pH will be around 3. And then what happens? If the pH equals the pKa, these two exist in about 50-50 mixture, right? It's a 1-to-1 ratio, because when pH equals pKa, the ratio of A minus over HA is around 1. It's the same. So what does that mean? Well, it turns out your stomach mucosa will readily absorb aspirin if it's neutral, because your cell membranes that are coating all of your cells that line your stomach, they easily absorb things that are uncharged. Anything that is charged, like this one over here, is going to have a much harder time to be absorbed, and it's going to take much longer to be absorbed. So taking aspirin on an empty stomach will facilitate its absorption through the membranes of the stomach, because the more neutral structure is the one that predominates under those particular conditions, okay? So the exact opposite happens with, for example, codeine. Codeine, shown here, contains this basic functional group, okay? So when there's lots of acid in your stomach, even at pH 3, it's still quite acidic for this compound, because the acidic form of this, the ammonium form of this compound, pKa is around 8, okay? So does it matter what the pH is in the stomach, whether it's 1 or 2 or 3 or even 4? This is the structure that is going to predominate, the acidic form of the compound. So codeine, if you take it orally, it's going to take a few hours for it to ultimately be absorbed. Why? Because it needs to transit through the stomach. Once it gets into the intestines, where the pancreatic juices are secreting neutralizing basic fluids that are neutralizing all that acid that's coming into the intestine, the pH in your duodenum and all these upper portions of the lower gastrointestinal tract, the pH in those regions is about 8 to 9. So that's going to be the point where even then only 50% of this is going to be released as the neutral structure. At pH 8, you have 50% of this and 50% of that, right? So that's the point. And when it starts going above 8, if it gets to 9, that's when this one predominates. That's when it starts getting absorbed, okay? So this is critically important in drug design, for example. If you want a drug that is absorbed quickly, through the stomach, you have to ensure that in the stomach pH, it's going to be neutral, because otherwise, if it has a charge of some kind, it's not going to be absorbed easily through the stomach. Then that causes a delay in when the drug is absorbed. If you in fact want the drug to, after you've taken it, for whatever reason, you need for several hours to pass so that the drug is absorbed slowly as it transits through the intestinal system, then you need to, again, design the drug in such a way that it has these acid-base properties so that it is absorbed properly, okay? So if you were to look at heroin and cocaine, for example, why do you think these drugs are not taken orally? These are recreational drugs of abuse that cause all kinds of problems in the population, as we all know. These drugs are not oral drugs. People who are addicted to these substances, they're not taking them orally. They're taking them either intravenous injection, which gets them to where they want it immediately, but otherwise it's typically snorted. And the reason is that it turns out, if you notice, like codeine, there's a nitrogen here and there's a nitrogen here in these two compounds. In the acid environment of the stomach, they would get protonated, and it would be hours before these compounds produce the desired effect that these individuals are looking for. They want their quick fix and they want it now, right? So when you put it through your nasal mucosa, it turns out the pH of these parts of your body are on the neutral to slightly basic, slightly above 7. So what that does is that the proportion of the neutral drug is much higher, and it gets absorbed much more quickly. So again, these are important physiological aspects of these concepts that have true and real life applications. In some cases, in true pharmacology. In some cases, it's having to do with more psychological aspects of things. But anyway, very important concepts when it comes to drug design, drug action, drug absorption, and things of the sort. All right, so we have about 15 minutes left. Any questions thus far? We're good? All right, so the last topic, if you notice, we're on slide 90 of about 112. We need to talk about buffers. Buffers is one of the most important concepts that we need to ultimately talk about in this discussion about acids and bases, because they're critically important physiologically. As I mentioned previously, when I was speaking about the ratio of A- to HA that depends on the contribution of multiple acids, this is where this comes in your physiological fluids. There's a whole bunch of acids, weak acids and weak bases that are in these fluids, and then what they do, which is what a buffer is, as we're going to discuss, they help maintain the pH of those fluids within a very narrow range, because that's one of the most important physiological functions of the body, is to maintain pH within that range. Otherwise, all kinds of bad things start to happen. So let's first define what a buffer is. It's a solution that necessarily contains a mixture of weak acids and weak bases. You can create a very simple buffer with just a single weak acid and a single weak base. This is what we would have done in the laboratory if we were able still to do that. But it can also be a complex mixture of weak acids and weak bases, which is what actually exists in your physiological fluids. But in general, it's a solution, contains weak acid and a weak base, typically in similar proportions. And then what that does is that it causes the solution to be able to resist changes in pH when a external source of an acid or a base excuse me, are added to that solution. Typically, we're talking about strong acid or strong base added to that system. And then what happens is that the weak acids serve to intercept any strong bases that come into the solution. And the weak bases, I don't remember if I said it the other way or the other, but the weak acids intercept the weak bases intercept the weak acids. And then what ultimately happens is that the overall ratio, this is the key, the overall ratio of weak acids to weak bases doesn't change by much. And if you remember that equation that I was talking about earlier, pH equals pKa. This is written in a slightly different way, plus, whoops, I have to erase it because I made a mistake. pH equals pKa plus the log of the ratio of the conjugate base to the acid. So what turns out to happen is that this ratio doesn't change much. If this doesn't change much, it ends up that this doesn't change much. Remember, this is a constant defined by each acid. If this is changing, this is changing because the pKa is a constant. So if what the buffer does is that it maintains a very, very small change in this parameter, ultimately causing a minimal change in this parameter. So one very important thing you need to be clear about, buffers do not maintain a constant pH. That is not correct. They maintain the pH within a very narrow range. There's still going to be some change, but it's going to be very minimal. And this is what the body does. It produces all sorts of buffers that end up in your bodily fluids, including your blood, inside of your cells, your urine, all bodily fluids. And any acids that may find their way into these fluids are quickly intercepted by these buffers, and ultimately that total ratio of bases to acids doesn't change much, and then ultimately pH remains normal. Okay, so ideally, the pH will change by not more than 1 pH unit. And so therefore, typically, when you're preparing a buffer in the laboratory, this is the key. When you're preparing an acid, a buffer in the laboratory, you want to choose the pKa of the acidic component of your buffer to be plus or minus 1 from that pH that you desire, okay? And what that ultimately does is that it really produces a good buffer that maintains that pH within that very narrow range. We're going to see how this works as we go through the discussion. Let me see what this slide is saying. Hold on, you know what? I'm going to have to open up let me just find the real slide on my slide deck so that I can read through it a little bit better, because that's just a jumbled piece of mess right there. Sorry, bear with me 1 second. I just want to find that slide, and it's this one. Okay. All right, so this is simply saying that what this slide is trying to say, that the behavior of buffers is going to be governed by this equation that I just wrote in that previous slide. So let me see if I move on to the next one, that's just starting to talk about a problem that we're going to go through. So this is the equation that I'm talking about that I wrote in that previous slide. So the properties and the behavior of buffers is largely governed by this equation. This is what is known as the Henderson-Hasselbalch equation. And again, my apologies that this is all jumbled here, but the Henderson-Hasselbalch equation is what it's called. So again, if you want to prepare a solution, this is how we use this equation. If you want to prepare a solution of a particular pH, I want to make a solution that has this pH, whatever that is. I need to pick an acid whose pKa is as close as possible to desired pH. And then what I have to do is mix the conjugate base of the acid and the acid at a particular ratio, such that when I calculate how much that has to be, calculate the log, add it to the pKa, it produces the desired pH. So what would be the ideal situation? If I mix these two in a 1-to-1 ratio, 50% of conjugate base and 50% of the acid, the ratio equals 1, the log of 1 equals 0, so therefore the pH equals the pKa. So this is what we say, that when you're preparing a solution of a desired pH, you should pick an acid whose pKa is as close as possible to the desired pH, because if you can find one that's exactly that, then all you need to do is mix these two in a 1-to-1 ratio. If you can't find the exact pKa of the pH that you want, but it's very, very close, then this ratio is going to be very close to 1. You just need to determine what it needs to be in order to prepare that buffer of that desired pH. So this is what we're going to do in the next slides. I want to walk you through. We have about 7 or 8 minutes. If we don't get through it, then we'll continue next week. But I want to sort of guide you through the process of how we prepare buffers in solution in the laboratory. So let's say you have a buffer that is made up of acetic acid and acetate. Okay. So this is just sort of going through the motions of explaining how the buffer actually works. I've been saying that your bodily fluids have bunches of acids and bases, and they serve to intercept different things that may come into the solution. Let's just simplify it to simply consider a simple buffer made up of, let's say, sodium acetate, in which the active ingredient is acetate, and then acetic acid, which is the acidic component. They coexist in whatever ratio. If they happen to exist at a 1-to-1 ratio, the pH of that solution will be exactly 4.74. pH equals pKa when that ratio is 1-to-1. Doesn't matter what the ratio is, whatever it is. If you add a small amount of strong acid, okay? So what happens is that small amount of strong acid is going to be consumed by the acetate. Okay, so now this has increased, and so the acetate picks up some of that H3O that was added from an external source. So the equilibrium is going to shift to the left. Okay, so this is going to go down a little bit. This is going to go up a little bit. And what that ultimately does is that the additional acid that was added from the external source, because the addition of that acid caused the equilibrium to shift to the left, ultimately the net amount of acid that results at the end of the process remains about the same. Okay, the ratio is altered a little bit. This goes down, this goes up ever so slightly. The ratio will go down a little bit. So the pH will go down a little bit, but as long as there's enough acetate to intercept any added acid, the ratio of the acetate to acetic acid remains reasonably close to what it originally was, and therefore that only causes a small and very minor change in the pH. Sort of the converse of that happens if you're adding hydroxide to the solution. So if you add base, small amount, you can't add too much because then the buffer is done. But as long as it's a small amount of hydroxide, the acetic acid that is present in that solution will intercept that hydroxide. Some of this will be consumed, more of this will be produced, so the ratio of acetate to acetic acid increases a little bit, but notice that this hasn't been pretty much altered much by the process. It turns out that the interception of this by the hydroxide only causes a small shift in the amount of hydronium that was present in that solution. Ultimately, again, the ratio doesn't change by much. The net amount of hydronium that was present in that solution doesn't change by much, and therefore the pH of the solution doesn't change by much. So it's the presence of these species in that solution. One can intercept bases, the other one can intercept acids. As long as it's not too much acid or base that's added, the net amount of hydronium that's present only changes ever so slightly. That's why it's called the buffer. If those two weren't present, then of course any amount of acid that's added increases the acid content tremendously. The pH goes down dramatically. Otherwise, the opposite happens if you add strong base. If you add strong base and there's no buffering species, the pH goes up tremendously because there's nothing to intercept that. Okay. All right. I think we can probably finish with this slide. So you have a solution, a buffer solution that's prepared using H2PO4 minus and its conjugate base, which of course the conjugate base will be HPO4 2 minus. So you have those two substances coexisting in an aqueous solution. It turns out these two substances turn out to be one of the primary buffers inside of your cells and in your urine. The pH of your urine is largely dependent on the ratio of these two things. So again, what is the reaction that results from the H2PO4 reacting with water to form its conjugate base? So this is the normal solution of H2PO4 dissolving in water. So when this is dissolved in water and it reacts with the water, It's going to transfer a proton to the water, and it produces hydronium, and then of course it produces its conjugate base, HPO4 2-. So if you add H3O, write the equation when H3O is added to this buffer. So when H3O is added to the buffer from an external source, what's going to happen is that this is the one that's going to intercept it, right? So the HPO4 2- will react with the H3O plus. That will then accept a proton from that, producing H2PO4 2- plus water. So some of this will be consumed, some of this one, which is that one, will be produced, right? The equilibrium shifts a little bit in this direction. So remember, this went up because acid was added, but this intercepted it. It shifts the equilibrium to the left. So ultimately what happens to this? It sort of returns back to the normal because some of the added acid was intercepted by this. That's what then leaves the buffer at the same pH that it originally was, okay? The sort of the opposite thing happens with, because we're running out of time, the opposite thing happens with the hydroxide. So if you add hydroxide, the hydroxide will be intercepted by this one. Some of this one will be consumed, some of that one will be produced, right? The reaction shifts a little bit in that direction. And then the hydroxide may have also consumed a little bit of this one, right? So therefore, it is replenished, and ultimately the pH doesn't change by much. So here's the critical question. What is the pH range at which this buffer operates? Well, you need the pKa of the acid to answer that question. And again, we said the optimal is pH equals pKa, which is 7.21, plus or minus 1. So it operates well anywhere between 6.21 to 8.21. Of course, the optimal operate is at pH around 7.2. Notice that that's very close to the pH of bodily fluids, which is around 7.3, 7.4. Okay? All right, so we'll leave it there for today. I have to converse with Dr. Geiger to figure out what we're doing with homework at this point, but just stay tuned to your email, and we'll continue as we did now next Tuesday. Everybody have a great weekend. Stay safe. Don't go out. Make sure you're stocked up and don't go anywhere. Just, be at home and be safe. We'll talk to you next week.